All right, great. Thanks so much. I'm Simone Ferraro from Berkeley Lab, and it's a great pleasure to be here today. So I'm going to talk about some of the recent cross correlations between CMB lensing and galaxies, primarily based on these three papers that we put out recently. So apologies if your favorite paper is not discussed here, but limited amount of time. So first of all, since we are going to compare to Galaxy Week lensing surveys and their results, let me give you one slide, a very, very simplified version of how they work. So what they do is they use galaxy shapes to measure shear. So as you can see on the picture here on the right, and they also measure galaxy positions. And they do this in a number of redshift bins that usually called the tomographic redshift bins. Then for each bin, you can form three 2-point functions, which are the autocorrelation of shear, which is usually known as cosmic shear, the cross correlation between shear and galaxies, usually called galaxy-galaxy lensing, and the autocorrelation of the galaxies or galaxy clustering. And then they're usually combined in what you'll hear called the 3x2 analysis. It really means three 2-point functions, as mentioned above. If you play a little bit with the algebra, you'll see that the parameter sensitivity, sort of shear, which is proportional to the lensing, cares both about the fractional matter fluctuations, but then it also cares about how much matter there is. So it's proportional to omega matter, while galaxy bias cares about matter fluctuations as well as galaxy bias. So if you try to make combinations that for which the galaxy bias is marginalized over, which is because we don't consider it as a fundamental cosmological parameter, you see that these combinations are primarily proportional to this quantity S8, which is sigma 8 times the square root of omega matter. And indeed, this is the quantity that galaxy lensing surveys are more sensitive to, as we'll see in the next slide. So let me give you a little bit of summary of status of the field about 1 year ago. And here I'm only talking about galaxy lensing, by the way. This is when I sort of got interested in this. So this is a nice plot on the left by Kids 1000 team, and shows several results as of 1 year ago in this sigma 8 omega matter plane. So first of all, you see that there's a large degeneracy, for example, for the SER1 between sigma 8 and omega matter, and that's because lensing really measures this perpendicular direction, which is this S8 quantity sigma 8 times square root of omega matter, and that's the direction with the least noise, and that's well understood theoretically why that's the case. And so you had, for example, the SER1 results shown here in yellow. Then you have some galaxy clustering measurements from Boss and Viking kids, and then kids combined. They always show the results combined with clustering. So that's the red contours over here. So while you see that there's a large degeneracy between sigma 8 and omega matter, this S8 parameter is very consistent between these different experiments, and it's consistently low. About 3 sigma low from the Planck results, which are shown here in gray. So here on the right, I just show the CMB results from Planck. For this S8 is 0.83, but that's not just restricted to Planck. If you take WMAP and add the BAO, for example, you get this same number. If you take WMAP plus ACT for the small scales, again you get something that's very consistent. So this I'm confident to call it kind of the CMB result, just rather than just Planck. And that you see it's kind of in all the 3 sigma tension with the lower redshift results from galaxy lensing, which at redshift a low redshift, but they are consistently low and very consistent with each other. So we thought, do we also have another form of lensing, which is CMB lensing, and can CMB lensing say anything interesting? Also because it has very, very different systematics from galaxies themselves. All right, so why CMB lensing? Well, first of all, I don't really need to introduce CMB lensing here, but you have map of primary CMB, which is statistically isotropic, and then you add a lens, and the lens and he has very, very much magnified effect as statistical anisotropy of the source, that then you can use this statistical anisotropy to reconstruct back what the lensing was. So CMB lensing, you can think of it just like galaxy lensing, except that a few differences. One is that it's sensitive to the entire observable universe with maximum sensitivity around redshift 2. The redshift properties of the source and then the redshift distribution of the source is very well understood. Is the primary CMB, so we have very little uncertainty there. You don't have problems with intrinsic alignment, shear calibration, blending, etc., that you have in galaxy lensing. And I would argue the impacts of systematics and foregrounds are relatively well understood, and it has comparable statistical power, as we shall see. So this is I think is a very useful probe of since we have this tension, it's like, can we say anything with using CMB lensing rather than galaxy lensing? Okay. So let me first of all talk to you about this paper a couple of years ago, which is the measurement paper. We used as a galaxy catalog, we use galaxies from the Unwise survey because it's the sort of largest full sky extragalactic catalog we could get our hands on, and as we'll see, it's also fairly high redshift. So essentially what we'll be doing is take a blank CMB lensing map, take various maps of unwise galaxies, and actually we had to work quite a bit to create extragalactic catalogs of mainly galaxies, and reduce all sorts of contaminants, stars, asteroids, anything that is in WISE. But what we could do is we could form 3 redshift bins, what we call the blue, green, and red. The redshift distribution is shown here, and so we have 3 tomographic bins, which have redshift. They peak at redshift 0.5, 1, and 1.5. So we fully cover the dark energy dominated era, and going deep into the matter domination era as well. So as overall is about 1 billion galaxies, and then they are cut down to a few hundred million by several purity cuts, and putting them in redshift bins. But anyway, so this is great. This two great catalogs that both are full sky. Of course, the galaxy is masked, and there are several aspects of this analysis. The first was characterizing the redshift distribution, because WISE does not have photoz's. So we did it in 2 ways. One is by cross correlation with spectroscopic surveys, mostly BOSS and eBOSS, that you see on the top row. So that's how you can get a redshift distribution. You can also cross match with the HSC and Cosmos redshift, and you get something that is very consistent. And in fact, the cross correlation redshift has the added advantage that it automatically takes into account the evolution of galaxy bias, so that comes for free, and that is quite an advantage for us, as we shall see. Okay, so without further ado, let me just jump into the results. So the top panels in these 3 bins are redshift 0.5, 1, and 1.5 again. I showed the galaxy autocorrelation. You see the error bars are here, but they're very small because, again, it's almost 1 billion galaxies. So the shot noise is really negligible, and so these points are cosmic variance limited, and you have almost a full sky. So that's why the error bars are so small. This is the cross correlation. The bottom row is the cross correlation of the galaxies with Planck CMB lensing, and again I showed that the errors are very small. In fact, this at the time was the highest significance, so the lensing detection of any kind, and you see the signal to noise here is in the sort of 60s, and once you combine it, it's very close to 100. So we expect to be able to say kind of your percent level precision on some of these cosmological parameters. So before any cosmological analysis, we wanted to make sure that these results were stable to a number of systematics. So for example, where you cut in a galactic latitude, how you get your redshift distributions, uncertainty on bias modeling, and restricting to particular parts of the sky, using versus not the systematic weights, things to do with magnification bias, scale cuts, etc., and using Planck TSZ free map, etc. And this is essentially just some proxy for the amplitude of the power spectrum. We did it in all the three bins, and certainly finding something that is consistent with our fiducial analysis. And most of the scatter, sometimes there is scatter of over the 1 sigma, but it goes in the low direction. It goes towards lower in the cross correlation. So as we'll see, it goes towards making this tension worse rather than better. All right, so once we were sort of confident in the measurement, what we did is we actually went ahead with cosmological analysis. So again, just one slide on sort of what that entailed. It was, well, first of all, we need the theory. We chose to, using effective field theory of large-scale structure in Lagrangian space. One particular implementation of that is this cleft. And of course, it includes magnification bias, and that's very important. Actually, it does change the results by more than 3 sigma, so it definitely needs to be included. And it's one of the things we spent a lot of time on, actually fully characterizing the magnification bias is non-trivial. Happy to talk about that later. Once we had that, and we had the bump powers, we made mocks with the same bias and roughly the same clustering, and a known cosmology and a variety of HODs, a variety of populating dark matter halos with galaxies. And we wanted to check that indeed we can recover, with our scale cuts and everything, we could recover unbiased cosmological parameters on the mocks before unblinding the cosmology. I remind you, this was all blinded to cosmology so far. So we chose, we made all the analysis choices based on being able to recover unbiased cosmology on the mocks. So for example, here the figure on the right shows for one of the samples, the green sample, sort of recovering the input cosmology on the mocks. As I said, the analysis at this stage was blinded to cosmology, and only when we were happy that for all the samples on the mocks we could reproduce the cosmology, and we fixed all of the analysis choices, then we went ahead and unblinded. The other thing that we had to do is figure out ways to marginalize of the redshift uncertainty. Is actually what I'll talk about is essentially what you saw. There some measurements from the cross correlation, and we had a full covariance matrix. So we generate samples of that, and we throw that in the chains. So it's fully marginalized over the redshift uncertainty. When you do that, it turns out you pick up a small noise bias for reasons we understand, and we have to subtract that. We have full covariance matrix of all the measurements, including the cross bin. So, the blue cross red bin, and the blue cross green, and the green cross red, etc. So we have full covariance matrix calculated analytically, and we've tested with mocks that agrees reasonably well. We check consistency between, then we unblind, and then we check consistency of cosmological parameters between the samples, and indeed we found them very consistent. So once we have consistent samples, then we can combine them in full results. Okay, so next I'm going to show you the sort of results for each individual sample. Okay, so the small contours are Planck in purple, and then the colored contours, the green, blue, and red are shown here. So individual samples, as you can see, they are fully consistent with each other, except the red is consistent with everything, but because of shot noise, is actually the sensitivity quantity is not great. So red statistically carries very little weight, but the blue and the green samples carry quite a bit of weight. And you see that when we talk about, for example, S8, they are fully consistent with each other. Since they're consistent, we can then combine them into a single measurement of S8 of 0.776 plus or minus 0.017. And you compare it with the 0.83 of Planck, and it's 2.6 sigma low. And if you remember the numbers, this was very consistent with the previous lensing surveys, as I show here. So again, here I have Planck in purple on the right, top right, and then showing the dark energy survey year 1. Remember that the year 3 was not out yet at the time, so that's why we show year 1. Then in green, we show our combined results, and kids is here, and you see they really lie on the top of each other, so it's fully consistent. And I remind you, this is a very good agreement with galaxy lensing, which is great news, but this is CMB lensing, right? So it's completely different systematics, and here on the right, as you showing it in this quantity S8, you can tell that this low redshift surveys tell a consistent story, and that's why it's becoming sort of interesting. So by this time I was quite beginning I was skeptical. I was like, oh, maybe we'll do CMB lensing, and we'll recover Planck, and then all is good, and lensing is hard, and who knows. But then there have been so here's where I really started to get excited and saying, we really reproduced the other surveys sort of low redshift result in a blind fashion, and so maybe there is something here to see. But we were we put these papers out, knowing that very soon we'd get the SCR3 results, which were much anticipated. So we put out our measurement. I say it was 0.776 plus or minus 0.017, and a few weeks later, the SCR3 comes out, and you can look at the number, and this is kind of a very amusing coincidence, and that's why I'm showing here. But you see, this is exactly the same number, 0.776, and exactly the same error bar, right? So of course, this is coincidence, and I found it amusing, and so of course I wrote to the DS team, and so all I want to say is, apart from the sort of coincidence, is that first of all, they are fully consistent with each other, and also is that CMB lensing is competitive with state-of-the-art galaxy lensing measurements. Of course, the analyses are a bit, they make different choices, so it's not exactly apples to apples comparison, but in terms of sensitivity, we are very close, and it will keep being the case in the future going forward. Okay, even in the sort of Rubin observatory era, CMBS4, for example, will have statistical power similar to Rubin in terms of just lensing alone. Okay, so we said the previous measurements are consistent. We are consistent, and year 3 is consistent with this picture of low amount of fluctuations at low redshift. So one thing that we have in common still is that we all use photometric redshift. So the natural question is it photoz's, right? And for that, we are very lucky that we are part of the DAISY experiment. That is an ongoing, getting close to the end of the year 1 observations, ongoing spectroscopic survey. So here is really, you're talking about spectroscopic galaxies. DAISY is gonna measure 35 million redshifts. So that's a factor of 20 improvement over SDSS. In 4 target classes, you have a very low redshift. You have the bright galaxies. Then you have the luminous red galaxies that are kind of if you want the easiest sample to use, they're very nice, very well so characterized. Then a higher redshift, you have emission galaxies, and finally quasars. So we have enough. So we've collected more than 7 million spectra. That's really enough to calibrate some samples, especially for the luminous red galaxies. So that's exactly what we did. We took the luminous red galaxies, divided them in 4 tomographic bins. And then we have a spectroscopic calibration of all of them. So basically, there's no redshift uncertainty on these bins. There's no tails. Everything is very, very well characterized, very close to 100% spectroscopic completeness. And then we also cross-correlated the samples with the Planck CMB lensing. So we did it in these 4 bins, and here is what you get for sigma 8. Just measured at that one more dependent. As you see, it comes and 30 sigma low, and this low should be here not significant to lower if the discrepancy prediction. Okay, so here is a plot that we had in that paper, which, by the way, were some of the first cosmological results from DESI. So that's I'm very excited to be part of it. And you can kind of see that there is like this interesting trend with in S8, which primary CMB is the highest, is a redshift 1000. The CMB lensing has maximum sensitivity at redshift 2 and is a bit lower. And then CMB lensing cross correlation redshift 1 with unwise lower. Then you go to kids at lower redshift, and finally DESI is the 2 dark green curves. Whether you include the first bin or not is the difference between the solid and dashed lines. And finally, BOSS also did full shape analysis of their just 3D. So there's no lensing there, just 3D galaxy clustering in redshift space, and also find something, the same redshift that is very consistent, although with very large error bars. So, full shape analysis of 3D power spectrum, as I said, also point to a low S8. And finally, combining 3D clustering and lensing cross correlations is really the way to go forward. And that's what we are looking forward to doing in DESI as soon as the year 1 catalogs are finalized. That really allows us to, for example, distinguish the effects of, say, modified gravity or new physics from a change of amplitude and from galaxy parameters such as assembly bias, for example, which shouldn't matter on such large scales that we're considering. However, it's great to check, and indeed that's what we were planning to do. Sort of as a warm-up exercise, some folks at Berkeley have done it recently. This is Stephen Chen, Martin White, Joe DeRose, and Nick Cochran, who took BOSS galaxies, so BOSS 3D galaxies, and they consistently jointly analyzed the 3D power spectrum and the cross correlation between the projected galaxy field and CMB lensing, and that also gets a value of sigma 8 or S8 that is low and in a 3 sigma tension with Planck. Okay, so just to summarize the status of the field recently, so here are, in blue at the top are various measurements from Planck. Here there are, after the first 3 points, these are all low redshift measurements, and you have DS and kids cosmic shear, so that's only lensing autocorrelation. You then have some auto and cross correlations. Then in the box, these are the 2 measurements I talked to you about with Unwise and DESI. And then you have some other combination, and the bottom ones are basically galaxy clustering alone, except the last point, which is galaxy clustering and lensing cross correlation combined. And you see that they're all in 2 to 3, even sometimes bigger tension. But to me, they all tell, a consistent story. And the story is, if, for example, even if you forget that they have comparable amplitude, the story is they all scattered one way, right? What's the chance that all these measurements, which are statistically independent, scatter all the same side? Then it's primary CMB. So of course there's cosmic variance on the primary CMB, so you should keep that in mind. But however, I think that this should be taken seriously, and you see, here's where you enter sort of more sociology of science rather than pure sciences. Is that some of the collaborations interpretation is, oh, it's only like 2.5, 3 sigma off, so it could be statistics, etc. But if you take it in a broader context and all of this measurement, and it's not only one probe, and it's all these various redshifts and very different probes, very different samples, statistically independent, etc. So I really think this is something we think we have a problem, and so my conclude with my 2 cents on this. I think we may have a serious problem, and it's worth paying attention. The problem could be either on our ability to measure galaxies, to measure power, interpret galaxy power spectra, etc. So either on the modeling side or on our understanding of the physics that goes in growth of structure between redshift 1000 to very low redshift, which is 13 billion years of evolution. So we may have some problem in our understanding of fundamental physics. So, there's no obvious common systematics because there are so many different probes. The one thing that is in common is we use similar tools to model galaxy clustering. So maybe galaxies are harder to model than we thought. These tools have been validated on many simulations, including some of your common, lensing, common mock challenges, blinded common mock challenges, and they've been validated and they've been shown to reproduce cosmology very well on simulations, but maybe the real world is more complicated than simulation. Who knows? Photosys, as we've seen, are likely not the cause because we now have a spectroscopy as well. There has been some discussion about possible projection and volume effects, which I agree they are tricky, and indeed we saw them in some of our analysis, but they are likely not the cause because they're present also in our mocks with the same parameter set. The same projections are happening in the mocks, and we don't see we don't see big biases in the mock, so they are likely not the cause here. Remind you that the neutrino-induced suppression for minimal mass is about 3%. Here we are talking about discrepancies of the order 10 to 15%. So it's too large to be explained by neutrinos alone, and those suppressions are on the top of minimal mass neutrinos that are already included in the analysis. So in fact, if you fit with neutrinos, you don't get a good fit because such large neutrino mass that you would need to explain a 15% discrepancy will mess up everything else, will mess up the BAO, etc. So neutrinos alone are likely not just the cause. Again, just the statistical fluctuation is very unlikely. Now there's many probes of that. It's on the other hand, it's hard to find compelling physics that can explain this because the expansion rate of the universe is very well measured at low redshift, so you have to change the growth of structure without changing expansion, which is sort of hard to do, and even most models will change both, and you can't do that. So the problem is worse on small scales. If you've been following the literature on this sort of lensing is low. If you go to nonlinear scales, the suppression, the discrepancy between sort of theory and measurements becomes of order 30-40%, so stay tuned. There's going to be a lot of measurements, and I think really this combination of 3D galaxy clustering and correlation with lensing will be able to tell us more in the near future. So I think I'll end here, and happy to take any questions. Thank you.